in the series of basics of software defined radios and practical applications lectures, we were discussing the distortion which has been introduced by power amplifiers and nonlinear component, and now we want to concentrate on some of the definitions which we have to know the specification of a particular power amplifier. So, one of the main thing of the power amplifier is efficiency of the power amplifier. Efficiency of any power amplifier is defined by the ratio of the output power divided by the input power given to it in the DC form. So, basically we have seen that whenever we amplify any input signal to any particular power of the output signal, this power is taken from a DC source. So, the ratio of the power taken from the DC source with respect to the power which we are getting in the power output is what we call power amplifier efficiency. Now, depending on where we apply our DC power, it can be called also drain efficiency, and symbol is given with a small d, or it can also be called the collector efficiency, and then the symbol contains a small c. So, it is in the case of solid state power amplifier which are based on field effect or bipolar transistors. So, if you come across the drain efficiency or the collector efficiency, most probably they are talking about the same parameter. Now, because we want to avoid the distortion in the signal, so we run it mostly in the linear range, and because of that we lose our efficiency, because we have known that as we increase our signal power, our efficiency of the power amplifier increases, but so does the nonlinear components. So, mostly when we are driving it in the linear region, then the output power can be given as the function of gain multiplied with the input power. In this definition, we have to note that the output power and the DC power, all the powers given here are in the watts, they are not in the logarithmic scale right now. That's why we are showing the output power as the multiplication of the input power with the gain and its ratio with the DC power consumed. Now, we can further modify this definition so that it can be given in terms of dBm, and when that happens, then what will we do? First of all, we will convert this into milliwatt by dividing by 1000, and then that milliwatt power we have to take this 10 to the power P and dBm divided by 10, so that we can get our input power if our input power is given in the form of input dBm. So, we can use this formula for the dBm. If we have watt powers, we can simply use this one. Then this PDC is simply the multiplication of the DC powers consumed by the system, which can be calculated by multiplication of the voltage and current values which is provided in the data sheet of a particular power amplifier. Now, that was the drain efficiency. Apart from that, you will also hear the term power added efficiency. So, what is power added efficiency? It is given with respect to the added power. What is added power? As I said, the output power takes its power from the DC source. So, when we say output power divided by with respect to DC, we are talking about all the power at the output. When we say added power, it means we are subtracting the input power from the output power, and then we have net power, which is the gain of the power, not the gain actually, but the difference between the power, absolute power which we have achieved. And when we give our efficiency with respect to this added power, then it is called power added efficiency. So, to clarify this thing, remember our original diagram of the PA. So, we had PDC, it is in watts, P out, it is also in watts, and P in, it is also in watts. So, ratio of this and this gives you efficiency, and if we subtract this power from here, so overall gain of the power we can say, although not, it is not division, it is in watts and it is in watts, then that ratio power added efficiency it is called. Now, we can rearrange the terms of this power added efficiency to give new definitions, so that we can define in terms of input power, output power of, or if gain is known, maybe in terms of gain. So, this second expression is simply we are substituting the definition of added power P out minus P in upon PDC, and if we eliminate our P in by using the formula that P in is what? P out divided by G, then we are getting P out 1 minus 1 upon G PDC. So, if we just know the gain of the power amplifier and we know the output power of the power amplifier and DC power, we can still calculate the power added efficiency there. Moreover, because P out upon PDC is actually the drain efficiency. So, if we know the drain efficiency and we know the gain of the power amplifier only, then also we can calculate the power added efficiency. So, in these all different forms we are able to calculate the power added efficiency there. That power which we have lost there, which has not been converted to the RF, that is what is called dissipated power. So, as the name suggests, it is the deviation of the power added efficiency from the DC. So, PDC minus P added power. Now, this added power is actually P out minus P in. So, PDC minus P out minus P in, it becomes PDC minus P out plus P in. So, if you do not know the power added efficiency and we want to know the dissipation of the power, this formula can define this. Now, dissipated output we can also calculate in terms of power added efficiency by playing little bit with these variations. So, what we can do that our we want to eliminate our PDC from the formulation and we just want to keep P out. So, let us use the formula, this formula, write down PDC as P out 1 minus 1 upon G divided by power added efficiency. Similarly, P in will be P out upon G. So, in this formula we substitute the PDC and P in value here. So, P dissipated at the output is calculated as PDC minus P out plus P in. So, let us put these values here. P out 1 minus 1 upon G minus P out plus P in, which is P out upon G. So, basically we are just rearranging these terms. P out 1 minus, okay, it is divided by P added efficiency. Okay. Added efficiency minus P out common and 1 minus 1 upon G. So, if I take common these two terms, then I will get this formula here. Or P out upon 1 minus 1 upon G and 1 minus at. So, by rearranging the terms of this, if you multiply this back here, this is the expression we are getting here. Now, in this case, if we say that our gain is much higher, then we can neglect this term and eventually the P out and the dissipated output may have this relation, but this relation exists only for very high gain. So, all these parameters are related to each other, they complement each other, and if you know one or two of those, the third you can easily calculate. So, let us have this example of the commercial data sheet. So, in this case I am showing you data sheet from the mini circuits, and they have two PAs of the same range. Basically they have very similar kind of parameters, but eventually with respect to frequency they are different. So, this is the example you will get for most of the power amplifiers. So, what it states, let us read it and then we will apply our knowledge of selecting this power amplifier. This is a power amplifier of 5 watt which works from 5 to 500 megahertz. It is saying that it has high output power of plus 37 dBm, which is the minimum value given here, and it can go a little higher than that, but they define the minimum values. Similarly, the high gain of 40 dB minimum they have said, so we should be able to get minimum 40 dB gain from here. Typically 4 dB noise figure has been said, and typically plus 49 dBm IP3 intersection point of third order is given. Now if you look at the particular specification, then the same thing, frequency and gain is repeated there. They have said that okay, it is a typical gain, but the gain flatness is plus minus 1.7. So it can be 40 plus 1.7 or it can be 40 minus 1.7 here. The output power at 1 dB compression is plus 37. So at 1 dB compression means our power amplifier has been saturated enough to get the 1 dB compression, and at that time the output power is plus 37 dBm. Of course we can compress it little further and we can get more output power. Noise figure is typical 4, IP3 is plus 49, VSWR values are also given, which is important for the matching, we are not discussing them here. DC supply voltage is given as typically 24 volt, but they can also be worked at 25 volt, but at the 25 volt they will have some deviation from the typical values. Supply current is given as 3.3 value. So by using this current and this voltage value, we can do the calculation of our PDC because of the power consumed by the drain or collector. Now if we see here, they are showing a drawing, mostly they give you the specification so that you have some idea of the packaging here. Dimensions are given so that you can put it in a particular place and you can design your space of the transmitter, how this will fit in your total schematic. They have some maximum ratings which should not be exceeded. Operating temperature is from minus 20 to 65 degrees centigrade. Storage temperature is from minus 55 to 100 degrees centigrade. Without any damage, we can give input power till 0 dBm, and it means we should not give any power beyond 0 dBm, it might burn. Now as I said, initially they have provided typical value, but with respect to frequency and with respect to applied voltage at the drain, they might change. So they are giving this data also so that we can select for a particular frequency, and correspondingly we can do our calculations. Also they provide the noise figure deviation with respect to different frequencies. Apart from that, they sometimes provide this kind of diagrams with respect to frequency so that you can have some idea, okay, gain is quite high near from 50 to 150 megahertz, after that it is dropping, near 300 megahertz it is quite low. So this kind of information helps us in selecting our device. Similarly, if we increase the frequency, we can say that output power is fairly constant near almost 40 dBm for most of the range, but at the high frequency range, when we are going from 400 to 500 megahertz, then it is dropping by. So we have to keep that in mind. So keeping this in mind, let's try some of the concept for the practical data sheet. Now first question you have to select, I want to use this power amplifier for amplifying a signal which has the carrier frequency of 600 megahertz. So can I use power amplifier? So let's have a look at our sheet, and it specifically says that it works from 5 to 500 megahertz. So at 600 megahertz it will not work like it has been proposed here. It might still give you some results, but it is not supposed to be working at 600 megahertz. So no, this power amplifier cannot be used for amplifying a signal at this frequency. Now the second query appears, suppose we apply input signal with the average power of minus 5 dBm, what will be maximum output power? So we are given the average input power. If you want to calculate the minimum output power, we should have a look at its gain characteristic, it will give us some idea. So what should be the minimum gain, right? So we are looking for the minimum gain here. So they have said that minimum gain is 40 dBm, sorry 40 dB, because it is a difference between the volt powers, so it is dB, not never dBm. So this is 40. So by this calculation, if minimum gain we can achieve is 40, input power is minus 5 dBm. So minimum output power we can get is minus 5 dBm plus 40 dB. So it becomes 35 dBm. So this is the minimum power we can get if we apply minus 5 dBm input average power. Now what will happen if we apply input power with this average power plus 5 dBm? So what would be the minimum output power? Now if we do the calculation for the C part, P out minimum will be 5 plus 40, which will be 45 dBm by calculation, right? But now let's have another look at our data sheet. If we see in this sheet, it is saying that input RF power which should be applied safely is 0 dBm, right? So plus 5 dBm power should never be applied. There is a chance that it will burn out. So we will say we should not apply plus 5 dBm input power, because it may burn, we might not get this power and we will lose our device. So no, it is not advisable that we apply this voltage, this power at all. What should be the input power for which the output power is compressed by 1 dB with respect to the output power if the linear portion of the power is exploited for high powers at 400 megahertz. So basically if you look at the this definition, they are asking what will be the output 1 dB compression point power at 400 megahertz, and what should be input power for that. So first of all, at 400 megahertz we have to find the 1 dB output power compression point. So D part says find P out 1 dB point and then calculate corresponding input power. Okay, so first of all let's read the output 1 dB power at 400 megahertz. So if we look at this list, at 400 megahertz output at 1 dB compression is clearly given. So as we had seen earlier, 24 volt is its typical applied voltage. Other than that, it can work at 22 volt also and 25 volt also, or in between also, but 24 volt is the given value. So if we read that this value 400 megahertz, we get 39.23 dBm. Now at 400 megahertz at 24 volt, what was gain? So let's have the look at the gain, and it is given as 46.18. So this is a small signal gain, linear region. So when we want to calculate this output power, it will be what? Sorry, input power. If you remember our formula for 1 dB compression earlier, formula was P out 1 dB point plus minus gain minus 1. So we do minus 1 dB here also, if you remember our formula. So it was P out is equal to input power at 1 dB compression plus G minus 1. For calculation of P out, we subtract this from this value. So input power at 1 dB will become 39.23 minus 46.18 minus 1. So it becomes 40.23 minus 46.18. So approx minus 6 dBm. So at minus 6 dBm we will have 1 dB output compression point at 400 megahertz. Now next question arises that can we use this PA in Antarctica at minus 40 degree centigrade for signal transmission? So if you remember, they were showing us, giving us the temperature range also. So minus 40 they have set in the operating condition. So it can work only from minus 20 degree centigrade to 65 degree centigrade in the operating condition. So no, for the signal transmission we cannot have this much, we cannot use our device for minus 40 degree centigrade. So answer is no for this one. How about in India in summer with 55 degree centigrade? So let's have a look again. Okay, so upper range is 65 degree centigrade for the operating temperature. So of course in India we can use it, but for in Antarctica we cannot use it at minus 40. So this is how we can select with respect to our temperature. Now what should be PDC based on given data? So the data is given here originally. Typical DC supply voltage and supply current is given as 3.3 ampere and 25 volt. So current is this one. Typical voltage, if you take 24, then you take V like this, and whatever supply voltage current is given to you. So suppose you are driving your P at 25 volt, then your calculation will be 25 into 3.3 because it is given as the RMS value. So normally it is defined there if it is RMS value or not, because DC value you will simply multiply those values. So V into I will give you PDC. So this is F portion. PDC will be VDC into IDC. Simply calculation because it is DC power. So VDC was 25 and it was 3.3. So 82.5, from calculation it is coming out to be 82.5 watt. Now what would be PA efficiency at 1 dB compression? So basically we have to know the P out at 1 dB compression, and because that is the definition of PA efficiency, normal efficiency. So output power in watt divided by PDC. This is the definition of the normal drain efficiency. So output power at 1 dB compression. So here we can see the output power at 1 dB compression. We are not given any frequency range. So let's take the typical one. So typically it is plus 37 dBm. So we have to convert that back into watt first of all. So it will become 10 to the power 37 minus 30 divided by 10, right? Because we have, first we convert from dBm to dB by subtracting 37, by doing 37 minus 30, now it is dB, and then that dB we are converting back into watts. So it will become, if you do this calculation, it is coming out to be 6.07%. So because we were not given any frequency data, we have taken the typical value. If we are given the frequency, then we can take the proper value. Now the next portion is at what frequency we can have the minimum noise due to power amplifier. So if you concentrate on the noise, minimum we have to select among these. So minimum I can see at 100 megahertz. So at 100 megahertz from the datasheet we can say minimum noise figure. And suppose you have to select your power amplifier in a way that you have to select your frequency range from 400 to 500 megahertz. So how can we get the maximum gain? By changing the bias voltage. So we are told 400 to 500 range is okay, our power amplifier can work in that, our system can work in that range, and we want to have the maximum gain by changing the bias voltage. So we have to have the maximum gain, so we have to look into this region here. From here to here we want to maximize our gain. So which is the maximum value here? So I can perceive that maximum value is 46.23, which is given at 400 megahertz and 25 volt. So last portion. So F should be 400 megahertz, and voltage condition VDC should be applied as 25 volts. So, by that you will have maximum gain of the 46.23. So, by using this kind of data sheets, you can select your power amplifier accordingly. So, in the next lecture we will see how we can combine different kind of power amplifiers to achieve a particular output power or a particular gain, and what will be the impact on its nonlinearity in that case. Thank you.